So I continue to make sense of these tables here. And now I've moved down to table 2.7.21, which is a rater measurement report. And I'm looking into the statistics for raters. In the same way, we have severity levels. This time around, the same column is actually referred to severity level of the raters, and that's I start from measure. So this is the severity level of the raters. There is a reverse relationship between measures and the total scores of the raters. The higher the total score, the lower the measure, because measure is the measure of severity level. So if a rater has assigned higher scores, like rater number 7, this simply indicates that this rater was quite lenient. That's why her scores were pretty high. And on the other hand, if a rater has achieved a high measure of severity, it indicates that this rater is less lenient or is severe, to use the technical jargon, compared with the rest of the raters. So yeah, this is only technical jargon really. It doesn't mean anything about the raters. It's just relative to other raters, this person provided lower scores to the presenters, whereas this person provided higher scores to the presenters, and that's all we can say about this analysis. Now, the other thing that we need to look at is in-fit, just like students, in-fit and out-fit mean scores, and this indicates whether the raters were reliable, and in other words, they were consistent in measuring students' performances. Now the thing is that this is an average indication, and one of the, of course it's important, but it's not the only indication as to whether the rater was reliable or not. So let's look at it as indication number 1, and this indicates that every rater that we have got on average falls between 0.5 of in-fit and out-fit mean square values and 1.5, the range that was also used to make sense of the student scores as well. So this indicates that on average raters are reliable, and that's pretty good news for our raters as well. However, we can also run another analysis called bias analysis, which can give us another kind of indicator as to whether the raters were biased or not. And I'll try to do it quickly for you in a minute. Before doing that, let's take a look at the separation and reliability statistics. The separation and reliability statistics for raters simply indicates that raters are reliably different from one another, and there are about 6 levels, unlike what I guessed at the start of this video. If you watch the previous video I made, I guessed that there will be around 3 levels of severity level which are distinguishable, but in fact we have 6 different levels of students, and that's quite high for 13 students in this performance. So that's very interesting, and this is exactly where the fair measure averages for students are useful, because with this level of difference and spread of raters based on their severity level, the scores could be quite different for different students, depending on what rater gives you his or her own rating. Your score could be different. Therefore, the average measure, the fair average measure, is quite a useful statistic here. So the other thing that I wanted to show you is bias analysis, and this surprises every rater, including myself, because at some point I realized that in some performance in the past I also had some bias, but I was never conscious and aware of that. But this kind of analysis identifies the bias. So you want to do bias analysis. I want to see if I put raters versus students, if there's any student to rater sort of bias, and I'm gonna get the output, and let's wait for the analysis to finish. I'm going to scroll down, and these are the biases that we have encountered. One of the things that we immediately want to look for is the probability of the p-values. Wherever we have a significant p-value, it indicates that there was some bias there. And first of all, let me just show you what I mean by p-value. So the p-value is represented in this column here, this prob, in this column here. As an example, student number 1 and rater number 5. This is rater, this one here, rater number 5 and student number 9. So rater number 5 scored student number 9. Is there any bias size? Yes, is 2.35 is the highest amount of bias here. On average, the amount of bias that we see is positive, and it's 2.35. In other words, the observed score, which was given by rater number 5 to rater number 9, altogether was 59, because there are 15 items, if you remember from the first video. However, the expected score, this is estimated by the model itself, is 53.31, and the differences between these two becomes actually bias, and then you convert this bias to logits and you get 2.35. So this means that on average this student has received a higher score than the rest of the people in this analysis from this rater number 9. But I don't see any other performances that are biased for number 9, so that's pretty fine. If the bias is just 1 or 2, it's fine. But sometimes in Many-Facet Rasch Measurement, you want to throw in what they call a dummy facet. For example, half of your student presenters are males and half of them are females. The very interesting analysis would be whether the gender of raters and the gender of presenters have any interactions, and so you can do a bias analysis to figure that out, and that always provides very interesting findings. Actually, in the 2 papers that I mentioned in the first video, we have run such an analysis, and we have found that there is a significant gender bias when it comes to oral presentations. Of course, in this class we can't do that because all the students are females, so we can't run such sort of bias analysis. So this bias analysis is just regardless of gender. It's just student versus student times rater kind of interaction analysis. Okay, so that's about bias analysis. So let me go back to the video and wrap it up for you. I scroll down because I only have 3 facets, so that's fine. For items, I would like to look at the items by difficulty here, by item, where is it? Okay, item difficulty is the first one. They have been arranged based on their difficulty, and as you see, the most difficult one is 1.11, and the easiest one is this is 1.11 logits difficult on average, and the easiest one, which is number 4, is minus 0.67 logits difficult. You can actually look at the total scores that these items have achieved. Naturally, when an item is very difficult, then the total score that it receives from the raters is lower compared with an item which is the easiest one, right at the bottom. Now, the other thing that we need to take into account here is the presence of at least, let me see how many misfits we have, so-called. So we have one item. Let me here highlight these 2 columns for you. We have one item here whose fit statistics falls outside of of the range of 0.5 to 1.5. So this indicates that item 3 didn't function properly. There is some noise in that item, we can actually track it down to find out what was going on in that item. You can look at the raw data and figure it out. Number 14 is also close to the borderline, but it's still fine. In other words, if I may use an analogy, I can hear more music than noise in this item, but in this item I start to hear more noise than music, and it's getting quite loud there. So what I would do is I would probably explore further to find out why item 13 is not a well-functioning item. And if I do not find a solution to that, I might have to remove it from the scale and run the whole analysis, because the scores and the reliability statistics and everything I have been discussing so far can be affected by the malfunctioning of this item. So in a reliable analysis, it would be better to remove the malfunctioning item and rerun the analysis if you can't really figure out what's going on. That's really a rule of thumb for Rasch analysis. Now finally, if you're interested, you can further scroll down and look at the scale. We need to get some hill shapes, something like a chain of hills. That indicates that because we have 4 categories, it indicates that the 4 categories had good thresholds. So this is the threshold between this point here. The threshold is between 1 and 2 is around here, and that's around minus 0.2 logis. So it indicates that if your ability level on average is about minus let's say 2, it's more than minus 2, let's say around here, then your chances are of receiving a 2 is higher than the chances of getting a 1. And in the same way, you can interpret this threshold between 2 and 3, which means that if your ability level is around, again here, right here, is around less than 0, is let's say minus 0.05 or something like that, minus 0.23 or so, then you'll stand to start to have a higher chance if you fall on the right side of the threshold then to receive a 3. So let me just reiterate myself. If your ability level is higher than around 0.5 or so, because that's the threshold point, in other words, if you fall on this side of the scale, you'll start to have a higher chance to receive a 3 rather than a 2 from your raters, and that should actually be realized in the actual ratings. But if you continuously receive lower scores than what you deserve, then that could be flagged as a misfit. And that's one of the good things about Rasch measurement, because when something is a misfit, it could indicate that you have received a score that you didn't deserve. It could be that you deserved a lower score, or maybe a higher score than the model expected for you. Okay, thank you very much for your attention. I think this video just wraps it up nicely. If you have any questions or any comments, please leave them in the comments section. I'm happy to read them and answer your questions. Thank you and have a good night.